So I need to do Latina. Okay. So a very good afternoon, dear students. So last class it was a bit rushed through because a lot of techniques are there and I need to cover those things. But I don't think I have done very much justice in last class because it is too many slides. But again, the slides are made quite clear. And just now I was inquiring, the slides are available to you, and therefore you can download it and go through it. And anywhere anybody is having any doubts or anything, then kindly mail to me, because I just have given all the matters so that you can go through the slides afterwards also and can clarify your doubts and could see it, what are the courses and how it is, and whatever questions or anything will come, that will be totally whatever are present in the slides. Okay. So now today it is the 4th class, and here again I will be covering this part. So application of voltammetry and other electroanalytical techniques. To expand it, so we will see the basic concepts of electrochemistry and electroanalytical methods, voltammetry and its application of inorganic and organic analysis. See, now electroanalytical methods are a large number. Out of that, normally voltammetry is very widely used, and therefore I have covered that extensively. Then thermal analysis, TGA, DTA with applications, DSC, which is differential scanning calorimeter with application, and finally the thermometric titrations. So again, here also it is like that. The slides are made quite clear so that whenever you want, you can follow them, you can look at them, and it will be all revised. And therefore, now let us go through the slides one by one. Just have a look. So in the basic concepts of electrochemistry and electroanalytical methods, electrochemistry deals with interrelation of electrical and chemical effects. It relates the flow of electrons to chemical changes. You all know this. So chemical changes triggered due to the passage of electricity and application of electrical energy and production of electrical energy due to chemical reactions. So now these are two different things. In one case, the chemical changes are the cause for electricity. And in another case, the electrical energy, or you are providing electricity to do a reaction. So based on this, there are two different types of electrochemistry. Now, electroanalytical chemistry encompasses a group of qualitative and quantitative analytical methods based on electrical properties of a solution of the analyte when it is made up in an electrochemical cell. So what are the parameters normally in any electroanalytical chemistry we see is the total charge, current, and potential. These are the three important parameters we normally look at. Now, what are the various advantages of an electroanalytical method? It is specific for a particular oxidation state of an element. For example, if you are taking a spectrochemical techniques like we have seen AAS or ICP-MS or ICP-OES, here if you are analyzing iron, so it will give the total iron. But it will not tell you whether it is iron 2 plus or iron 3 plus. This information, these techniques cannot give. But here in electroanalytical chemistry, you can get that also. So it is specific for a particular oxidation states like cerium 3, cerium 4. You can separately know how much cerium 3 is there, how much cerium 4 is there. Unlike in case of ICP-OS, where you will get total cerium. Instrumentation is relatively inexpensive compared to around 20 to 30 lakhs here to 1 CR in case of ICP-OES. They provide information about activities rather than concentration of chemical species. Limit of detection can reach to the level of sub-nanogram or sub-ppb level, appreciably high sensitivity, and characterize like informations like stoichiometry and etc. also can be known for electrochemistry. So the basic concepts of electrochemical cell, let us see here. So a DC electrochemical cells consists of two. You all know this, so I will not go very deep into this. You know what is a electrochemical cell and what is a electrolytic cell. So here the electrodes are there. They are conductors like metals, conducting carbon materials or semiconductors, etc. And what can be an electrolyte? This is the ionic conductors like salts, acid, alkaline, water. So with this, there is a conducting solution. There is an electrode. And then if these two solutions are separated, then they should be joined by a salt bridge. So this is an electrochemical system. And the purpose of the salt bridge is to isolate the content of two halves of the cells while maintaining electrical contact between them. So this is a typical electrochemical cell. And here it is a galvanic electrochemical cell when the copper sulfate and is there in the thing. So electrochemical cells can be galvanic cell or can be electrolytic cell. So what is galvanic cell? It produces the electrical energy at the expense of chemical energy. So this is the difference. Galvanic cell produces electrical energy at the expense of chemical energy, means some chemical reaction will take place in which flow of electron will be there and therefore generation of electricity will be there. But here in case of electrolytic cell, chemical reactions occurs due to passage of electrical energy. So this is the basic difference between these two. So examples are, here it is battery. So when you are putting some battery into your mobile phone or anything which is running due to battery, so battery, there is a redox couple reaction will be there, and because of which your energy will be provided, electricity will be provided to your electrical unit. Let's say it is a mobile, then mobile, and then after that you can charge it again. And when you are charging it, it is becoming electrolytic cell. Chemical reaction occurs due to passage of electricity. So it will be regenerated that time. And if another example I can give, then it is commercial production of sodium. This down cell or chlorine, alkyl electrocell, aluminum, these are all electrolytic cell example. So this is the representation of these two. In one case, here you need a battery, means here you need a electrical energy supply. Here you don't need a one. So now the thing says anode, cathode, salt bridge, and electron flow. What is the anode? The anode is the electrode where oxidation occurs. Cathode, the electrode where reduction occurs. Salt bridge, so it used to maintain the neutrality. And electron flow always from anode to cathode through the wire. So electron flow will be always from anode to cathode, and therefore electricity flow will be from cathode to anode. So through the wire. And E cell also you might be knowing what is E cell is defined as E right minus E left. So I have written everything extensively. When you are going through the slides, since you are getting the PDF, so go through it, please go through it so that you can have a better understanding. Now, schematic representation of cell. Normally, in many cases, you must be seen that all are not written. It is written, some cell is written like a representation. So what does it mean, this type of representation? So I have just given a typical formula A, B, C. A is for anode, means here we will write the anode. B is for salt bridge. So this double line means salt bridge, and C is cathode. So you have to write the cathode in the right side. So like this, so by convention, a single vertical line indicates a phase boundary or interface where a potential develops. The double vertical lines represents two phase boundaries, because in salt bridge, you have seen there are two, this is a salt bridge. Here there is an interface of salt bridge and solution. Also here there is an interface of salt bridge and solution. And therefore, this two line is there for the two boundaries of the salt bridge. So whenever it is there, it is a salt bridge present. So this is a typical representation. So here it is the anode present in the left side, cathode present in the right side, and in between the salt bridge is there. And cell potential is E right minus E left. or E cathode minus E anode. These are all are the representation. You can have a look to this. So the important equation in case of electrochemical reaction is the Nernst equation. For a typical reaction like Mn plus, by taking n electron, it is getting reduced to metal. For this is the electrochemical equation. So you have E0 minus 2.303 RT by NF log M by reduced form by oxidized form. So this is the typical electrochemical reaction, which after putting all these values is, if it is a one electron system, so this is your system, it is an electron system. So this is the, when it is one electron, only 0.059. If two electron, then again by 2. So accordingly it will go. So with this electrochemical things, there are many methods are there, electroanalytical methods. If I want to subdivide it like this, it is a tree of various electrochemical methods. You can have a look. Here are many things are there: interfacial methods, bulk methods. Then in interfacial, again static and dynamic. Here it is conductometry or conductometric titrations. Now in static method, potentiometry, and here in case of your dynamic method, there are various things: control potential and constant current methods are there. So in this control potential, one comes voltammetry, which is very widely used, and therefore we will look into this. So what are the quantities normally we play with in case of electroanalytical technique is current, potential, resistance, conductance, quantity of charge, that is Faraday, F, then time, volume of standard solutions, mass of an mass of the electron depositing species, and all. So with playing with all these things, you can calculate the analyte concentration. And in case of voltammetry, it is voltage and current relationship. So what is a voltammetry? I have given the definition here. Voltammetry comprises a group of electroanalytical methods in which information about the analyte is obtained by measuring the resulting current as a function of time-dependent potential. So you go on applying potential, because of which there is changes in your analyte, and therefore there is changes in the current. And so from the current potential relationship, you can know what is your species and how much it is present. Now, three important experimental parameters in voltammetric technique are potential applied at the working electrode, measurement of current, and stirring and non-stirring experimental solution. Whether you are stirring the solution while doing the experiment, or are you not, it is a static or dynamic system. So that is what the stirring and non-stirring means. So now a typical voltammetric cell looks like this. This is the electrode connection. These three are. This is the cap of the cell, and here it is a reference electrode. Now, reference electrode can be taken, as you may be knowing, your calomel electrode is there, silver chloride electrode is there, which all of these cells, the potential is known, and therefore they are used as the reference cell. Now this is the working electrode, where actually your analyte is getting reduced or oxidized, and this is the counter electrode, and this is the electrolytic solution. So three electrode systems normally are used during voltammetry or any measurement. So normally till now you have seen cathode and anode, but in case of voltammetry, we are taking three electrode system because it greatly improves the precision and reproducibility of your electrochemical experiments. So therefore, we are normally keeping a reference electrode also in presence of your working and along with your working and counter electrode. So why three electrode system is needed in this type of measurement? I have explained it here clearly. Normally the connections are like that. The potential circuit is between voltmeter, working electrode, and your reference electrode. The potential circuit is there, so that the potential of your working electrode is being kept constant. And now your current circuit is between your working electrode and the counter electrode. So this is the current circuit. So, and there is a potentiostat is joined between your counter electrode and working electrode, so that the working electrodes potential will not change very much, because we want to work in a particular potential sometimes, and then we are applying some potential. So there should not be a drag, or whatever potential we are applying should remain constant and fixed. So these two are the potential start is attached here, and there is a reference electrode with respect to which we are measuring the potential of working electrode always. And since current is not flowing between the reference electrode, so its potential is fixed. So then with reference to this, we can measure the potential of the working electrode. Now, polarography is a particular variety of voltammetry in which normally we use a dropping mercury electrode, then it is called as polarography. The first important voltammetric technique to be developed is polarography. This uses a dropping mercury electrode. When there is a dropping mercury electrode, that voltammetry is known as polarography. It is working electrode. Current is measured while applying a linear potential ramp. So this is now, you can see, you are applying a potential, slowly increasing potential with time, and accordingly you are measuring the current, and this is the type of curve you are obtaining while doing the measurement. So this is a S-shaped curve, and here this is the equation I max or I average. So here the various terms are written here, which terms are there. So you can see here, and this is the concentration. So from this you can calculate the concentration, because all the other things will be known for your system. So you can calculate the C, and current you are measuring. From this you can calculate your concentration of the analyte. And this E half is the half of the potential curve. This is the particular, like specific for a particular species of an element. So this will give you which is the element. If for say iron 2 plus it will be different, then iron 3 plus also it will be different. So then you depend by knowing the E half, you will be able to know the which is the species. Now normal polarography has been replaced by various forms of pulse polarography, because to go to lower level or to have better detection limit, the normal polarography has been replaced by various pulse polarography. So what is the type of potential applied and how that current potential curve looks like, I have given it in details. The A, that means this one, is normal pulse polarography, where you are going on applying a pulse of voltages. Instead of a linear ramp, now you are applying some pulses. So how does it help? It helps in improving the height of this polarogram. Okay, so then there is differential pulse polarography, where now there is a ramp. Based on the ramp, now you are giving the same pulse. So this will now, and the measurement here is, here once you are measuring the current, and you are measuring the current once here, and the plot is between change in current to potential. Here it is only current to potential, it is change in current. So here you will be obtaining a peak shape curve. So now you can see this one will represent this peak of the curve. So now here it is more sensitive, and it will give a better thing, because it is difficult to know the peak point here, whereas it is clear. So this is the difference. Third one is staircase polarography, where it is like this. Your voltage will be like staircase. Slowly it will increasing. So here also it is current versus potential. You will get this type of plot. And here square wave polarography, where again the pulse will be increasing slowly, so that the ramp will be there, and you will get this type of curve. Advantage of square wave polarography is that we can make the T very small, as small as 5 millisecond compared to 1 second for other forms of pulse polarography. So which significantly decreases the analysis time. So this is the advantage of your square wave polarography. So now it is whenever we are using a metal electrode, then it is the hydrodynamic voltammetry. use of a solid electrode in place of a dropping mercury electrode. The solution is stirred mechanically during the analysis using either a stir bar or rotating the electrode. Hydrodynamic voltammetry uses the same potential profile as in polarography, such as a linear scan or differential pulse. The resulting voltammograms are identical to those for the polarography, but the difference is only here it is a metal now you are using instead of a mercury. And the hydrodynamic voltammetry is not limiting to mercury electrodes. It is useful for analytes that undergo oxidation or reduction at more positive potentials. Okay. So this is the difference between your hydrodynamic voltammetry and polarography. In polarography, exclusively it is a dropping mercury electrode or a mercury electrode, whether it can be static mercury electrode drop also, but it is mercury. But in other cases, it is a metal electrode. Now there are stripping voltammetry also, where there is anode stripping voltammetry, cathode stripping voltammetry, and adjusted stripping voltammetry. So what does that stripping voltammetry means? Here, if your analyte concentration is very, very low in ppb to sub ppb range, then what we will do? You first give a potential to reduce the analyte, and they will be reducing and forming an amalgam with the mercury. Then after few seconds, you allow say for 1 minute or so deposition, and then you again strip it, so that now all those analyte will be pre-concentrated in a small volume of the drap, so that your concentration will increase, and you will get a proper signal when your analyte concentration is very low. So there are three types: anode stripping, cathode stripping, and adjusted stripping, depending on the voltage you apply. So now I have given some examples which are used for what? This anode stripping voltammetry. These are the elements normally. These typical examples, many more may be there. I have just given some typical example. This is cathodic stripping, all these analytes. And adjusted stripping, you can see adjusted stripping is mainly organic molecules are there. So now it's the details. In any case, whether it is a anode stripping or cathode stripping, what is happening? First, you apply some potential for this much time. So in this case, what will happen? It will all deposit, and then you strip it back. So now you see copper 2 plus is becoming copper, so getting deposited in mercury as an amalgam. So after that, you again scan the potential, so that the mercury amalgam will again come to copper 2 plus. So now here we will get some signal. So this signal is because of this. So now you will get here. So when you are depositing now, see, typical deposition time of 1 to 30 minutes are common, depending on the analyte concentration. If your concentration is very, very low, then you can allow 30 minutes also, so that you can get a better sensitivity to detect your analyte. So this is also again in the second step, we can scan the potential anodically, that is towards a more positive potential, and therefore you are getting a signal. Now it is cyclic voltammetry. So I have not taken here the adjunctive and cathodic stripping voltammetry, because anode stripping is most widely used, and the other two are also similar type. Therefore, I have explained only one type. Now cyclic voltammetry. What is cyclic voltammetry? Here in cyclic voltammetry, we complete a scan in both the directions. So first you have to like this, both the directions you need to do your scanning. So we first scan the potential to more positive value, resulting in the following reaction. So when you are going, so your reduced species will reduced. R means reduced, O means oxidized. So reduced species will go to its oxidized species, and few electrons will be ejected out. And the potential reaches a predetermined switching potential. So you have to first enter what will be the switching potential. So after it reaches the switching potential, we reverse the direction of the scan towards more negative potential, and then now your oxidized species again will go to the reduced one. So here this is the equation. the peak current in cyclic voltammetry is given by the Randall-Sevick equation. So here it is given, where N is the number of electrons in the redox reaction, and A is the area of working electron, D is the diffusion coefficient, and it has been written C is the concentration of the electroactive species. So if when you are giving a faster scan rate, so you normally get equal and opposite reaction, because now you are scanning the voltage in one direction and then taking it. So these two type of plots are equal and opposite. However, if when you are a slow scan rate, sometimes the back peak does not present, because when it is slow only you are scanning, the product may not it may not be totally reversible. It can react with some other species forming something else, and therefore this peak will be totally absent, so that you can know whether your reaction is reversible or irreversible. So at the slower scan rate, however, the peak on reverse scan may disappear. One explanation for this is that the products from the reduction of R on the forward scan have sufficient time to participate in a chemical reaction, which products are not electroactive. So therefore, it can be. So by doing this too, you can know various properties of your product. Now,
excuse me, ma'am.
Yeah.
Ma'am, can you please go back to the last slide? I have a question from it.
Yeah.
Is cyclic voltammetry in principle the same as the hysteresis loop that we obtain in the magnetic experiments?
Actually, your voice is not clear. Slowly you speak so that I would be able to hear.
I'm asking if the cyclic voltammetry in principle similar to the hysteresis curve and all those things we get in the magnetic experiments.
Magnetic?
In principle. Yeah, in principle, because it's scanning one way and then scanning the other way and seeing the differences in the two.
So there is no magnet involved here?
No, there is no magnet involved here. I'm asking if this is in principle similar to how hysteresis loops are obtained.
Yeah. So actually it is not clear what you are actually asking. Can you just mail me?
Okay, ma'am. I'll ask
You just
mail.
You have noted down mail ID, right?
Okay.
Yeah, you just mail me, so that, because your awaz is breaking. Okay?
Sure.
So amperometry means your constant potential is applied to the working electrode and current is measured. So as a function of time, so you apply the potential will not vary. You apply a fixed potential, and then with time you go on measuring the current. So because now we are not varying the potential, so it will not that whatever will come, it will not called as a voltammogram. It will not come as a voltammogram, but some plot will be there. So one important application of amperometry is in the construction of chemical sensors. One of the first amperometric sensor was developed in 1956 by L.C. Clark, measured dissolved oxygen in blood. So you know the oxygen concentration in blood is very much important. So to measure that, whatever electrochemical sensor is there, it all based on, actually all the electrochemical sensor are mainly based on your amperometry. So this is the given here. You can see clear picture has been given. This is the cross-sectional view of your electrode and electrode tip. So it is a circular electrode. Here there is a platinum disc electrode is there, and which is your working electrode. Okay, and there is a silver ring electrode, which is your reference electrode. Now, one application of your this electrochemical technique I can say here is the uranium in ppb level. So you know uranium in seawater is present around 3 ppb level, and many efforts has been taken to concentrate it. And I have given this typical example because anyway uranium is very much important for DAE, and therefore I have given this example. So ultra trace concentration of uranium have been determined using adaptive tripping voltammetry Now you can have here, there I have shown you the anodic stripping. Now it is adsorptive stripping. What is done, and we normally seen that adsorptive stripping voltammetry, all the organic molecules are there. So here also uranium can be complexed with chloroanilylic acid. So it will form a complex, and then it will be absorbed in your cathode, in your working electrode, and then will be stripped back. So this is called as adsorptive stripping voltammetry, and detection limit is around 100 nanogram per liter. That is 100 nanogram per liter means 100 ppt. Parts per trillion, 100 ppt. So advantage of voltammetric technique, I have listed it down, and you can have a look to it. So there are many advantages are there. So I did not read each and everything, just you can go through it. Now let us now look into the thermal analysis. So this is also an important technique, thermal analysis. So now thermal analysis refers to a group of techniques used to study the physical and chemical properties of materials as a function of temperature or time under control condition. So these techniques measures changes in properties such as mass, heat flow, dimension, and mechanical behavior when a material is subjected to heating, cooling, or isothermal conditions. So you may be knowing, in case of electroanalytical technique, it is all about electron flow, voltage, current, and all. And now in case of thermal analysis, it is like function of temperature. You need to see the mass change, heat flow, or any phase change is there. All those things can be seen. So common thermal analysis techniques are TGA, that is thermogravimetric analysis, differential scanning calorimeter, which detects the heat flow associated with phase transitions, and melting or crystallization. You know all this process of phase transition or melting or crystallization, they are all an electro like heat absorbing or like endothermic or exothermic reactions. So these things can be known. Then DTA, differential thermal analysis, then dynamic mechanical analysis, and thermomechanical analysis. These two are not very widely used. However, these three are very frequently used in thermal analysis. So just to give you a feeling what are the various thermal analytical methods can be, I have listed here the name of the method, the symbol, and the property which is measured. So at a look, you can know what are the things, because in many times you will find the acronyms only. So from the acronyms, and if you correlate with this table, then you can know what is that. So it is thermogravimetry, derivative thermogravimetry, differential thermal analysis, difference calorimetry, and what are the property are being measured here are listed here. Normally TG, DTG, DTA, DSC, and evolved gas analysis. These are very frequently used than other things. Still the table has not ended here. It is here also, there. So you just can have a look to it. So while carrying out this measurement, the furnace atmosphere can be either static or air or continuous flow of gas, like purging. So this, like anyway, whenever you are doing a thermal analysis, means some furnace is involved. So it is a very small furnace with milligram quantity of your sample, and that any of these experiments can be done in 3 modes. In one case, it is a static mode, either air or a continuous flow of gas, whether it is purging. So either you can take static air flow, inert gas flow. Anything can be done. Inert gas, nitrogen also can be taken, or argon also can be taken. So where inert gas is needed, it is because to inhibit oxidation. Because if you are passing air, then oxygen will be there, and at high temperature with oxygen, there can be oxidation. So if you do not want your sample to get oxidized, then you need to have a inert flow. And if you want to maintain a reducing condition, then definitely hydrogen gas needs to be purged. So now thermal analysis is all deals with your thermodynamics. So normally this is the equation, which is the Gibbs-Helmholtz equation. It is the most important one. And for a normal this type of reaction, when we are heating a system, if two things we have mixed and then heating a system. So and you know that this reaction is spontaneous only when delta G is less than 0. And at equilibrium, delta G is equal to 0. And so these thermodynamics things you must be knowing. So any thermal analysis method is closely associated with your thermodynamics. So this thermal analysis it involves the monitoring of spontaneous reaction. And this is what is important. Now, what is thermogravimetric analysis? It is the study of weight change. Thermogravimetry, as the name suggesting, thermogravimetric means temperature and weight change. So weight changes of a specimen as a function of temperature or time. The temperature is increased at a constant rate for a known initial weight of the substance, and the changes in weight are recorded as a function of temperature at different time interval. So this technique is useful strictly for transformations involving the absorption or evolution of gases from a specimen consisting of a condensed phase. Now this evolved gas also can be analyzed by either an IR or mass spectrometer, and that is what is called EGA or evolved gas analysis. Now a plot of mass versus temperature is known as the thermogravimetric curve or thermogram or TG curves. It permits the evaluation of thermal stability, rate of reaction, reaction processes, and sample composition. How sample composition? Because now at what temperature, what is evolving, if you are analyzing, say, a compound you have taken, which initially when you have heated it to 100 degrees centigrade, it expels some moisture. Then there will be some weight change, as water has a molecular mass of 18 grams, so it will be relating to that. So and then even you are having a EGA, if you are having a IR or a mass spectrometer, there also you will be able to know, okay, moisture has been released or it is a water molecule. Then after that, on further heating, whether if CO2 is getting involved or something like that, then finally you will be able to know what can be the compound is, if these are the things getting involved by heating your sample. So this is what is done. Now the temperature induced transition. So several physicochemical processes can occur with increasing temperature, like dehydration. It can be dehydration, decomposition, oxidation or reduction, phase changes, etc. So TG is concerned only about the temperature induced processes which leads to change in mass. Weight gain, if on increasing the temperature, weight is gained, that means your sample is absorbing something, and by that it may be getting oxidized. So either of these two processes, oxidize means absorption of oxygen. So by any of these two processes, there can be weight gain in your sample. Weight loss means it can be dehydration, decomposition, something has getting evaporated, or disruption. So these processes are involved with associated with weight gain, and these are the processes which are associated with weight loss. So this is a typical thermogravimetry diagram showing variations of mass with temperature. Now if this is percentage weight loss and this is temperature, if initially it is 100, the weight loss percentage, there is no weight loss, so it is 100%. With increasing temperature, it can be like these are three different compounds just to show you how it can be shown. So it is the thermogravimetric plots. Now say if your plot looks like this in a thermostat, this plot, if what can be the different time, here it is three different types are shown, here many more types are shown, and I have written down if this is the type of curve you are getting, then what can be your inference by initially looking at it. So first one, the sample is thermally stable. Since you can see there is no weight change throughout the temperature, this is the mass and this is the temperature. So throughout the temperature, no weight change is there. That means it is thermally stable in the scan temperature. Second, if there is initial mass loss is there, see, this is initial decrease is there, this area. So initial mass loss is characteristic of desorption or drying. It may be your moisture or anything. So that is initial mass loss will be there. Single stage decomposition. See, there is one change in mass. So it is a single stage decomposition because initially it is decreasing and then again constant. There is constant. There is no initial change, so there is no moisture or anything. It is constant up to a quite a good temperature. Then suddenly one and then again constant. That means it's a single stage decomposition. Multi-stage decomposition in this case because there are multiple mass losses are seen. So it is a multi-stage decomposition. Then multi-stage decomposition with relatively stable intermediates. Why? Because here it is after one decomposition, it is stable for quite some time. Again, decomposition stable for quite some time. So it is a relatively stable intermediates. Then multi-stage decomposition with no stable intermediate product. So now you can compare this with this. Here decreasing, again there is no stable phase. Again it is continuously decreasing with some harm. So it is a multi-stage decomposition with no stable intermediate product. The effect of heating rate must be considered. So here you need to do the experiment once more with a slow heating rate to get much better ideas. Okay. So in this case, it is gain in mass. So due to reaction with atmosphere or oxidation of metals or anything can be, but this is just a typical example I have given. So if something like this you are getting, so there is an increase in mass. Oxidation product decomposes again at high temperature because initially it is increasing, so there can be an oxidation and then again it is decreasing. So again it is getting decomposed at high temperature. So this is just I have typically given some types of plot what can be obtained when doing a thermogravimetric analysis and what should be your initial first look inference. And then you can have multiple different experiments to exactly know the composition. So this is a typical, I have shown a typical like your balance and then block diagram of thermogravimetric system actually. So this is where is your reference standard is given and this is your balance. Here it is the reference sample, this is the furnace and this is the your balance beam. This typically commercial instrument looks like. So now the balance, what is a balance? Because since you are measuring a weight difference, you need to have a balance. The basic requirement of an automatic recording balance includes accuracy, sensitivity, reproducibility, and capacity. Recording balances are of two types, null point and deflection type. The null type balance, which is more widely used, incorporates a sensing element which detects a deviation of the balance beam from its null position. Because when it is this the null position, so any deflection from this, so there will be a sensor which will detect the deviation and triggers the restoring force to bring the balance beam back to the null position. So that, and then the restoring force will directly proportional to the mass change. So this is the typical principle of your thermogravimetric analysis. So now here also I have seen the different orientation of the sample relative to the furnace. So the sample can be like, see, this is the furnace horizontal arrangement. This your balance can be placed this, or it can be placed like this, or it can be placed like this. So these are the various positions depending on these various advantages are there, and many OEM or the instrument manufacturers, they can have multiple type of furnace keeping facility, or many instruments are having a single type of furnace keeping thing, and each and every position has a particular advantage or disadvantages. The suitable sample for TG are solids that undergoes one or two or any of the two type of reaction, या तो एक mass loss or mass gain, which I have already told you. So now that processes which occurs for melting of a sample, but there is no change in mass. So you cannot do it by TG. So for TG, it must be there is some change in your mass. The factors which may affect the TG curves are classified into two main groups: instrumental factors, there's furnace heating rate and furnace atmosphere. Definitely furnace heating rate is there, and furnace atmosphere, I have told you, either it is a static atmosphere or you can pass air or you can flow argon or nitrogen, or sometimes if you want a reducing environment, then you can flow hydrogen also. And sample characteristic, weight of the sample and particle size of the sample. So now instrumental factor, this is, if you want to elaborate it a bit, then the temperature at which the compound or sample decomposes depends upon the heating rate. Okay, if you heat it very fast, then you would not be able to get a proper peak, because then there is some mass loss, balance is getting imbalance, there is from null position some restoring force acting to make it balance, and then how much is your restoring force, depending on that it is calculating the mass. So if you are going to heat it very fast, then what will happen? All this process will not be properly getting calculated by the instrument, and therefore you will not get a clear picture. So heating rate is very much important. The decomposition temperature is also high. A heating rate of 3.5 degrees centigrade per minute is usually recommended for reliable and reproducible TGA. So you have to need to keep this in mind. A heating rate of 3.5 degrees centigrade per minute. The very, very slow heating rate. You need to, it is usually recommended. Furnace atmosphere, the atmosphere inside the furnace surrounding the sample has a profound effect on the decomposition temperature of the sample. Pure N2 gas from a cylinder pass through the furnace, which provides an inert atmosphere. Either you can pass N2 or even argon can also be used, but argon is much more expensive than nitrogen, and therefore you can always use a nitrogen gas when you require an inert atmosphere. Now, weight of the sample, if considering the sample characteristic, a small weight of the sample is recommended. Using a small weight eliminates the existence of temperature gradient through the sample, because now I have shown you the furnace. So furnace is there, your sample will be here. If you are taking large quantity of sample, then what will happen? When your furnace is heating your sample, now the side of the sample will be heated very fast, and inside it will be cooler zone. So the sample has to be very, very small, and it is 1 milligram of sample is typically taken. So small sample weight of the sample is recommended. Using a small weight eliminates the existence of temperature gradient through the sample. Particle size of the sample should be very small and uniform. The use of large particle or crystal may result in apparent very rapid weight loss during the heating. So these things you need to keep in mind while doing a thermogrammetric analysis. Application of TGA, if we need to say, then what are the applications? Thermal stability and purity of a material, oxidative stability of material, composition of multi-component system, then sublimation behavior of various substances, decomposition temperature and kinetics, estimated lifetime of product, moisture and volatile content in material, or the used in studying your catalyst. If some catalyst you need to study that with temperature how it is behaving, then that also can be done. The change in chemical states of the catalyst can be found out by thermogrammetric analysis. So now few milligram of sample. These are the optimum conditions. Only few milligram of samples, thin layer of sample, open sample container. Because anyway, whatever gases are evolving or moisture is going, you have to allow them to get lost. So there should be open sample container. It cannot be closed, because then there will be no weight loss. Okay, because everything will be inside. Inert gas flow, slow heating rate. So this is a typical example of calcium oxalate decomposition. This is the calcium oxalate. When first it will lose a water molecule, then on more heating it will lose a CO, carbon monoxide, then it will be carbon dioxide. So this is the cycle which you can corroborate with your TGA curve. See here, this is one weight loss, second weight loss, third weight loss. So this is H2O, this is your CO, and this is your CO2 loss. So accordingly, this is a typical example I have given because calcium oxalate is a very known and compound, and you can imagine how it changes, and therefore you can correlate with these reactions, and therefore I have given this typical example here. So now this is a derivative thermogravimetry. Now TG is there where you are getting this type of curve. If you take a derivative of this, means now in case of weight, you have to take the delta weight or delta M. Then again, as you know, when you are taking a derivative, so this type of curve will be converted to, if you are taking its first derivative, then this will be converted to this. With this point, it will correlate with this point. So now the exact temperature where change is happening, here it is difficult to know. When it is a sloping curve, you have to find out the middle point to know the exactly where the change is happening. So which can be known by DTG in a better way, because now it is a peak shape. So this point you can identify from this plot, and exactly where the transition is happening, you can know from this plot. So this is a TG and DTG diagram in a single plot I have shown you. Now DTA analysis. What is differential thermal analysis? This technique involves the measurement of the temperature difference between the samples and a thermally inert reference material. So now it is differential thermal analysis. So there only sample you are taking. Here along with sample, you will be taking one reference material, and with that reference material, how its mass is changing. So you need to see that. So inert reference material, when both are subjected to identical thermal regime, heated or cooled in a constant rate. DTA techniques respond to enthalpy changes for almost all reactions, irrespective of whether they are accompanied by mass change or not. So even if mass change is there or not there, it does not matter. Now what you are looking is with respect to the reference material, how its temperature is changing. So that is differential thermal analysis. The material under study and the inert and reference material are made to undergo identical thermal cycles. So both the sample and the inert reference material, both are provided with the same thermal cycle. Any temperature difference between sample and reference is recorded. In this technique, the heat flow to the sample and reference remain the same rather than the temperature. So it is the heat. You know what is the difference between heat, H, enthalpy, and temperature. So that is like in the prior to this also I have told you that thermodynamics has a great role to play when you are dealing with thermal analysis. So like this, the heat, which is normally quantity of and this is the temperature. So difference you need to see that in this technique the heat flow to the system and reference remain the same rather than the temperature, because you know if a material has higher heat capacity, then it requires more temperature to get raised to the same temperature, right? More heat to reach to the same temperature. So now see the differential temperature is then plotted against the time, against the temperature DTA curve or thermogram. So you you have started heating, and now it is melting is there. So it is a dip in the curve. So there is a melting, because you know melting is a endothermic reaction. And when so it is a dip in the, so crystallization is a exothermic reaction, melting is a endothermic reaction, है ना? So like that, in some cases either it is a crystallization or then it is a melting. It is a so in case of when you are taking dq by dt, so it is a melting and it is a crystallization. So depending on that, your exothermic and endothermic, you can have a look to this. Now the phenomena causing changes at heat or temperature. Now what are the physical phenomena and chemical phenomena? So this I have made a list of it. You can go through it. Adsorption is exothermic, disruption is endothermic, and like that oxidation is exothermic, reduction is endothermic. So you just can have a look to know it. Now this is a typical commercial DTA instrument look like. So what is the DTA curve? Is typically the T sample minus T reference. So that is the delta T, the T sample minus T reference against the time or temperature. So in the absence of any reaction in the sample, what will happen? T sample minus T reference will be 0. So this is the baseline. It will be the baseline signal. And if it is below, then it is endothermic. If it is above, then it is exothermic curve. So now the reference material, what can be used as reference material? I have given it here, magnesium oxide, aluminum oxide, or silicon carbide. These are the typical reference material used in case of DTA. And characteristic of the reference material, whatever used in DTA, it should not undergo thermal events over the operating temperature. It should be inert towards sample holder or thermocouple. Its thermal conductivity and heat capacity should be similar to that of sample. So now DTA application, quantitative analysis is done, analysis of polymers, ceramics and metal industry, phase transition. Sulfur has many phases, so you can study the phase transition of sulfur. So all these things are typical application of DTA. One example, again the same example, calcium oxalate and water is given here. So if there we have seen the TG curve, here you can see the DTA curve of that calcium oxalate, and for that, so for this reaction, this will be the peak, and for this reaction, this will be the peak. So around 200 degrees centigrade, this is happening. Then around 800 centigrade, it will be decomposing. So when it is in air, so there will be some intermediate will be forming, because if it is without the air, then calcium oxide. With air, it will be forming your calcium carbonate. And nitrogen atmosphere, the above process is endothermic. So I have given the example, and all you can have a look to it. Then copper sulfate, typical example of copper sulfate and 5 water. You can have, this is the DTA curve for copper sulfate, and the reactions also I have written it here, because all the 5 water in case of copper sulfate is of different type. 2 waters are outer sphere, and then 3 waters are inner sphere. So first outer sphere water is getting lost, then again 1 water, and then again 1 water. Slowly it is like this. Now difference between TG and DTA, I have listed it here. You can go through it. Change in mass of sample with increase in temperature. Measure the temperature difference between sample and reference with increase in temperature. So change in mass gives information about change in sample composition, change in thermal stability, change in kinetic parameter. Whether here the plot is delta T versus temperature, and maximum and minima gives information about exothermic and endothermic process associated with the sample. Now differential scanning calorimeter, DSC measures this is a typical flow sheet for a differential scanning calorimeter. And what is it? It measures the differential heat flow associated with transition in substance and reference material linearly heated at a predetermined rate as a function of time and sample temperature in a controlled atmosphere. Now here the atmosphere is kept controlled. This measurement provides quantitative and qualitative information about physical and chemical changes that involve endothermic and exothermic or change in the heat capacity. So actually that is the DTA analysis and DSC analysis goes bis and bis. So DTA analysis is suited for the determination of characteristic temperature, while differential scanning calorimeter additionally allows for the determination of caloric value, such as heat of fusion, heat of crystallization, like that. Both DSC and DTA samples and reference both are heated or cooled at a constant temperature linearly at predetermined rate. So this is what is DSC and what is DTA. It clearly tells about, this slide clearly tells about that. So during any thermal event in the sample, the system will transfer heat to the sample or from the sample pan to maintain the same temperature in the reference sample. So there will be a reference sample and your sample. When there is any thermal event, then the temperature needs to be, they will try to keep the temperature same. And there are two basic types of DSC instruments, power compensation and heat flux DSC. So both the differ fundamentally in their instrumentation, otherwise and principle wise, but instrumentation is same, but in principle they are the different, and they want to always, they have a tendency to match the temperature with the reference sample, and therefore whatever heat is lost or whatever heat is gained will be that signal will be coming to you. So a typical differential scanning calorimeter. So now this is the typical DSC curve of a polyethylene terephthalate. You know PET. PET is a polythene. PET bottles you may be using at home. And some PET bottles of your water bottles are also made up of PET, polyethylene terephthalate. So this is the typical DSC curve in that. So according to the this is the melting point, melting temperature around 250 degrees centigrade is there. Now next comes the thermometric titrations. The thermometric titration is defined as titration in which end point is determined by measuring the heat generated during the chemical reaction. So normally thermometric titrations are also used extensively for various materials. So what is the principle of thermometric titration is that titrant is added at a known constant rate to a titrant until the completion of the reaction, which is indicated by a change in temperature. So there is a continuous measurement of temperature, and the end point is determined by inflation in the curve generated by the output at a temperature measuring device. So when there is a change in temperature, so that is the end point, and you can now know that. So consider the following titration procedure, where A is the titrant and the corresponding number of moles. You know, a typical reaction like this means this indicates the number of moles here. Now B is the analyte and B is the corresponding to number of moles. Now P is the product, where P is the corresponding number of moles. Again, in this type of reaction also stoichiometry is very much important, which we have read in our initial classes, and there is some heat generation. When it is plus means it is an exothermic reaction. It is written minus means is some endothermic reaction. So at completion, the reaction procedures, a molar heat of reaction delta HR, which is shown as a measurable temperature change delta T. So in an ideal system where no losses or gain of heat due to environmental influence are involved, the progress of reaction is observed as a constant increase or decrease of temperature depending on whether delta HR is negative, indicating an exothermic reaction, or positive, indicating an endothermic reaction. So this is a setup, typical setup of your thermometric titration assembly. So this titrant, this is a water jacket, but it needs to be a particular, its temperature should not change the temperature of your air vessel, and therefore it is passed through a water jacketed, and then there's some stirrer is there. So finally any change in temperature it can monitor, there will be inflation at the end point. So application of thermometric titrations again is the similar to your normal many titration. This you can have your potentiometric titration also. You can have this type of titration by using indicator normal from burette to the pen also, and in thermometric titration also, because you know any acid versus your base titration is a exothermic reaction. So there is some involvement of temperature change. So with this also you can, this type of titration also you can do by thermometric titration assemblies. Wherever there is a heat change involved, that type you can do with thermometric titration assembly. Boric acid versus NaOH, calcium and magnesium titration of calcium, magnesium versus CDTA. That is, this means typically it is known as complexometric titration. So all this type of titration, which we have seen that normal with burette and pipette also we can do by using an indicator. or we can do by using your potentiometer also. Since these all are associated with some temperature, some heat change during the process, so this can be done by thermometric titration also, because while doing this type of analysis also, when you are using a acid and adding a base to it, or using taking a base and adding acid to it, you must be feel the change in temperature in your hand when you are doing this. So that means when you are feeling the change in temperature, that means heat change is involved in that. So now it can be done by thermometric titrations also. So this is the typical plot is there. So similar type of plot only you will be getting. So there is a change in temperature in this, and volume of NaOH added, change in temperature, again volume of NaOH added, change in temperature and volume of NaOH added. So these are the typical thing. And now this is the equivalence point whereas in case of normal acid-base pH measurement or potentiometric measurement, this becomes the endpoint. But here you can see this is the you're representing the endpoint is there. So this is all about these classes. And anything, if anybody is having any, kindly mail me your doubt so that you will get an extensive answer, because here sometimes either your voice is not clear, or without using any aid, I may not be able to explain it here properly. So anything, any doubt you are having, kindly let me know in my mail ID, so that I'll also feel good to answer your things, and with I can take references from different books to make you understand in more clear form all the things. And at the same time, because all my slides are made quite clear, if you go on reading slowly also the slides, you can understand the things very clearly. And I have in the first class I have given you the very reference book name also, from which I am following, so that and which is available in net for download, and you can download it and go through it also. Okay. So any doubt, like anything, anybody wants to tell something? Because till now for the second assignment, I have not received the response of everybody. So I request you all to kindly send me the assignment report.
Ma'am, there are only 3 assignments till now, right?
Yeah.
So which assignment are you referring to?
Yeah.
Which assignment are you referring to?
In the first class, regarding the solvent extraction, which for one step, if you are using, like say you are having 10, if you are extracting some analyte in a single step, and if you are doing it in multiple steps, so what will be the percentage extraction? That derivation I am talking about. So I have received from around 10 to 12 persons, but yet to receive many more, because I was looking, it is around 80 persons are there in the class. So I am yet to receive from other persons.
And ma'am, I have a question. Since you are unable to hear me clearly, I posted it in the chat.
Which
Are
one?
you able to hear me?
Yeah.
Are you able to hear me clearly now?
Yes. Tell me.
Yeah. So I had a question that should we refer to AR West solid state chemistry for the TGA and DFC section, or is there better material available elsewhere?
Actually, in the first class, I have written down the book, name of the book, which I have followed. In my first lecture, I think I just, in this lecture, I have not written actually. Next lecture, I will give you the book name, which is actually available, which is available in Google. You can download it. It is a book, a big book of analytical chemistry, some foreign author, and it is quite clearly mentioned all the things, all the electrochemical techniques and thermal techniques, everything chapter wise it has given in a very easily understandable language. So I will give you in my next class. Okay.
Okay.
Okay.